Hello and welcome to our next set of stats notes. We're on section 10.1. So we're doing our first of two sections from chapter 10. In chapter 10, we're going to be looking at data that's quantitative data that is related, has two different variables or aspects we'll look at. First way we're going to look at that is with correlation. So when I study the relationship between two sets of quantitative data, it's often helpful to construct some kind of graph called a scatter plot. And then by creating the scatter plot, we can look for some kind of correlation between the two variables on the set of data. The correlation exists when the values of one variable are somehow associated with the values of another. A lot of things have associations, so the amount of time it takes to make a product or the amount of man hours versus the price of the product, the more time it takes to make it, the more it's going to cost. The distance you want to ship something versus the cost of shipping it there. The more the distance, more it will cost. There's lots of things that have correlation. So correlation exists when values of one variable are associated with the values of another variable. Sometimes one thing going bigger can make the other go smaller. So maybe the more an item costs, the less of the item you'll probably sell because not many people are going to be willing to buy that said item the more you drop the price. Here we have an example. So this is two different sets of data, the age of a car versus the price of a car. So we're looking at one specific car model and we're saying, well, if you sell it when it's only 1 year old, it's probably going to sell for like $8,500. If you sell it, it's 2 years, someone sold it for when it was 2 years, sorry, 4 years old. I'm looking at the wrong one. 5 years old for $8,500. Someone sold one for when it was 4 years old for $103, $103,100. Someone sold one for 6 years old for $7,000. So you can see how the price fluctuates, but each time you can see in the general trend that as the age got longer, the car got older, the price of the car was generally less. And so this would be an association. There's an association between the age of the car and the value of the car, how much you can sell it for. And this is where we're looking at, this is what correlation deals with, is trying to look at this trend, this connection between two different variables usually that are connected. One of the things we want to do with this is we'd like to draw a line that best fits the data. We want some kind of line that kind of follows this trend and shows us how good it is. And it's nice to use some kind of straightedge, maybe try and line it up a little bit. It looks like if you kind of cross it through here, somewhere where it's going to hit most values, you want kind of almost as many above as you do below, maybe something like this. Now this isn't perfect, right? Because we're just kind of guesstimating. There are ways to get the best line. We'll talk more about that in section 10.2. But if you have a line that's trying to match the data, you usually think about what shape it is. This one I drew a straight line because this looks pretty straight. Some lines will actually have curves. So this line would be a linear line, linear or straight. Sometimes the line that best fits it will be a curve. And you can see from this that since it goes down as you go to the right, that as the age increases, the price decreases. So as the age increases, the price decreases. So again, we're not going to focus on how to get this line right now. We're going to more focus on how good this line is. In the next section, we'll focus more about how do you get this line in the first place? How do you get this line of best fit? Well, we'll say this is the line of best fit, but again, it might not be because we just drew one. So I'm going to put a little question mark. So that was kind of our best guess, just freehanding one. And again, if we think it makes sense to do this a straight line or a linear graph, straight line, a linear correlation exists. So we do have a linear correlation when there is a correlation and the plotted points can best be approximated by a straight line. So there is some kind of correlation and it looks like a straight line. So that's what we call linear correlation. So we're going to be dealing with linear correlations in this section. We're not going to get really into the other types of correlations in this class because that's more advanced statistics. We're going to keep it simple and just look at straight line correlations. So if there is a correlation and it can be best approximated with a straight line. That's what we're going to call linear correlation. Okay, now if you're going to make a line of best fit, it's useful to be able to measure how good that line fits, how strong that correlation is. So the number statistic we use most commonly to measure that correlation is the linear correlation coefficient R. So that's the typical value we use. How good is the correlation? How strong is the connection? So it measures the correlation between the two variables. And that's going to be that correlation coefficient R. A lot of people call this the Pearson product, because it's named after the developer, Carl Pearson, but we're just going to call it the linear correlation coefficient. That's what we'll use. So this shows a couple different graphs, and then actually gives the R value for each. So if you draw a straight line that matches this data, this one would have a positive correlation coefficient because it goes up to the right of 0.859. This one has a negative because it goes down to the right of negative 0.971. This one you can see is not really a nice straight line, and you can see that the correlation coefficient is really small. The closer to 0, the less correlation there is. You'll see that the things with more correlation are going to be bigger. They can be bigger in the negative direction. The negative just shows that it goes down to the right instead of up to the right. And then if there's no linear correlation, you will see that a line won't really make any sense. Again, it's going to be very low value for R typically. Though in any really case, if you see a curve like this where it's not a straight line, where if it's a curve, then you really just ignore R completely, because R is really just designed for straight lines. Now, if you want to calculate R, to get the value R, this is the way you calculate R. So this is the way we measure how good the linear correlation is. This is the calculation, the computation formula. We're never going to use this because it's just long and big and huge. We'll let calculators use it. Basically, at this point, we're going to say that doing this by hand is a waste of time. It's very tedious. So instead, we'll just let the calculator do the computing. But this is the formula it will use. So that is the formula to compute R. And it's all this. And you can see there's a lot of sums. So they're going to have to do things like add up the products of all the x's and y's, which would be the variables x's and the variable y's, add up all the x's, add up all the y's, add up all the y squared, add up all the x's squared. So there's lots of adding things up. And then the more dots you have, the more you have to add up. So this gets really long and time consuming. This one doesn't really lead to any understanding. It's just the best way to get the best answer. It might be more helpful to look at this calculation. So this is not a great computation formula because it would give you lots of rounding error. And again, we're not really going to worry about either formula because we'll just use a calculator. But this one shows you kind of what's going on here is they're taking all of the z sub x's and z sub y's, which would be z-scores for the x and z-scores for the y from their sets, and multiplying them all together, and then adding that all up and dividing by 1 less than the total. So it's actually kind of the average of the products of the z-scores of the two different values of each variable, so the x value and the y value. So that's one way to think about this, is that it is multiplying z-scores and then finding their average. The value R is a statistic. Remember, statistic means that it's worked based on sample data. So when you calculate R, you're just calculating for a sample, not for the whole set, which means it's not the value for the whole set. The parameter, the value for the whole universal collection, the whole population, is actually this Greek letter rho. So the parameter rho is actually what we measure for the whole set. That'd be the entire population. R is just a statistic based on sample data. So we'll actually see later that we'll use R when we calculate from our sample, and then kind of make estimations about what the parameter value rho is for the entire Greek. It looks like P, but it is the Greek letter rho, not a P. It's kind of a little weird curve here. So that parameter rho is the value for the entire set. Okay, so let's actually find the linear correlation coefficient for a set. Oh, sorry, before I do that, let's talk more about what things we can expect with that value. So a couple things to know about this linear correlation coefficient R. First off, it's always between -1 and 1. You can kind of think of like a percent. It's like how much of a percentage is the correlation, with -1 being like negative 100%, so it'd be a straight line, down with 100% correlation. So you can see how every dot's right on the line, that'd be -1. And then 1 would be positive 100%, so that'd be positive, it's going up to the right, and every dot's on the line. So those would be the most extreme values. You could go from 0 to 100. You can't go past, because either no correlation, which would be 0, or complete correlation, which would be 100%, or 1 or -1 if you're going down to the right. So value is always going to be between -1 and 1 inclusive, so it includes all those. The value R does not depend on the scales used. So if you use different scales here, if you count by 5s or 10s or 1s, it's not going to change it. It's not going to change what R is. So you can't like tweak it by changing the scale. So it does not depend on the scales. The value R is not affected by switching X and Y. So if you take this graph and you switch which one's X and which one's Y, so you end up with flipping that over on the diagonal basically. It wouldn't affect anything. You're still looking at the same correlation. So it doesn't matter which one's X and which one's Y. You can swap the variables. You still get the same result. So not affected by switching X and Y. The value R only measures linear correlation. It is meaningless for anything else. So if you have a curve, not a straight line, then R doesn't mean anything. So it only works. R only measures linear correlation. Only use it as a straight line. So I always want to make sure you're working with a straight line before you try and figure out what R is or use it for anything. It's very sensitive to outliers. So if you have outliers, you don't really want to use R. This is just a value that works when you don't deal with outliers. So again, you can see perfect correlation, where the value is 1. You can see pretty strong correlation, like 0.9. So you can see there's definitely a general upwards to the right trend. So that's positive, strong correlation. Here you can see the correlation is pretty weak, but you can kind of see a general trend up to the right. So that's why it has 0.4. The more weak it is, the more spread out it is, the less it looks like a general trend, the smaller this R value would be, closer to 0. Here this is the same thing, only negative. So perfect negative is going to give you -1. This is pretty strong correlation to the down to the right, so that's be -0.9. And again, this one's pretty weak, so it's kind of weak correlation. That's -0.4. So you can have positive or negative. Negative just means the direction it's going down to the right if it's negative. So you're going to be negative, things to be positive. Okay, so that's kind of what R is. So let's calculate R. Like I said I was going to, but I forgot about that stage. Okay, again, we're not going to actually use the formula, so let's skip that. It says use the computing formula. Let's use technology instead, because the computing formula is super tedious. It's a lot of calculations. And there's nothing I'm going to make you use it on, so you might as well just use technology instead. So we're going to actually use the ln reg of a plus bx. That's the thing we're going to do. We're going to have to put these in our data, so we're going to put list 1 and list 2. Again, you can swap list 1 and list 2. It won't affect anything. We'll put that in our calculator. So we're going to go to the stat edit. I already put these in here, but you're going to have to go in and type in. So you're going to type all these. First row will be your first list, and then the second row will be your second list. They should be the same length because there's matched values. Each one of these has two matched up and down numbers, so they should be the same length. Once you get that all typed in, you get stat, and you get calculate. And you'll look down and you'll see number 8 is ln reg a plus bx. There is a ln reg ax plus b. You don't want that one, you want the a plus bx. So just make sure you're using the right one. So the ln reg a plus bx. So then our x list will be the list 1, because that's the first list up here. The y list will be list 2. You want to make sure that you leave the frequency list empty, because we don't have frequencies, we just have these given values. So the frequency list, make sure that entry is blank. Mine actually had a list in here before I started doing these notes. I had to clear it off. So I have to come down here and hit the delete key and clear that out. And then you can hit calculate. And it gives you A and B, and you go, wait a second, Mr. Hochbeil. I thought we were looking for R, and that's what we were looking for. But I wanted to show you that sometimes if you don't have your calculator settings right, you won't get R from this. So right now I'm not getting the value I need. I did get A and B, but I didn't get R. So where'd R come from? Well, what happens is there's a mode setting that determines whether or not this actually gives you the R value. So to fix this, so R is calculated. We're going to have mode. So I'm going to hit the mode button right there. There's mode. So we're going to have mode. And then you're going to go all the way down to where it says stat diagnostics. So it says stat diagnostics. You make sure that is on. So stat diagnostics. On. So if you reset your calculator, this always gets shut off if you reset your calculator. So if you do, you have to go back in here and turn it back on like I had to do on mine because mine had been reset and I lost it. Now if I go to stat, calculate, do that linreg, a plus bx again. Now when I calculate that, it should give me r as well as r squared. It actually gives you both. So it actually will give me both r and r squared. So r squared is 0.8396. We'll talk more about r squared in the next set of notes, so you don't have to really worry about it for now, but it is nice to know where to find it. So doing this linreg a plus bx will actually get you r squared as well as r, which is negative 0.9163. Those are the values that don't show up unless you have the stat diagnostics turned on. Now that you have that, now you can find out what r is. And so you can see this one has a negative linear regression. Now, you do want to be careful because doing this, just punching numbers in, get an answer, you can get a linear regression even if the dots don't make a nice line. So before you do any of this, the thing you should always do first is graph it. Now, if you try and graph it as is, it's probably not going to show up very well because it's not doing your stat graph. So make sure you go to stat graph, make sure that's on. And you want the scatter plot, which is actually the very first type of graph. So you can see it's got dots on the graph. That's what you want. Make sure your lists are list 1 and list 2, because that's where we put the data. And then you should be able to hit graph. Now mine's still not showing up. Why is that? Well, because it's not zoomed in properly. So you always want to make sure when you're doing stats graphs, hit zoom stat. So zoom 9. And now you can see it. And you can see now this is mostly a straight line. That's why I got a pretty strong correlation, right? Negative 0.9 is pretty strong. It's not quite negative 1, or which would be 100%, but it's fairly strong. You can see the R going really well. So this is strong negative correlation. And that makes sense, right? The age of it is going to get larger, then the price is going to go down. That's what we graphed. We graphed age versus price. So if you think about your cars again, lots of things, as they get older, typically the price goes down until you get to the antique range. But up to a certain point, as the age increases, the price decreases. So that's using that linreg a plus bx. That's really the only calculator function we'll need for this section, because again, that gives us r pretty easily. So that's the main thing we'll do in this section. I guess I shouldn't say the only. We have one other thing to do. But if you want to find the r value, if you want to find the linear correlation coefficient r, you use the linreg a plus bx, and I'll give it to you. So you do have to type this data in your stats list, and you have to make sure that this stat diagnostics is turned on. Okay, some warnings about this. I mentioned these a little bit in passing, but we'll definitely want to make sure we cover them here. First thing, you've got to be really careful using the linear correlation coefficient. You always want to check that you have a linear set of data first. So when we went in there and put in that data and looked at the thing, you want to make sure this is linear. So if you graph it and you get a curve or something, then you know that R doesn't make any sense. So be careful. Always first check the scatter plot that shows a linear trend. Otherwise, any conclusions you make from this correlation don't mean anything. If it's a curve, it's useless. Curves are useless. So that's what you got to be careful with. Again, you can't use this for R if it's a curve. If it's a straight line, you're good to go. Next thing. A lot of people have heard about statistical studies and stuff, and things where people say this is causing that, or this is causing whatever. You got to be really careful about thinking about causality when you see connections. So when we talked about the age of the car and the price of the car, people say, oh yeah, the car is older, so that makes it worth less. And that's a causality relationship. And when you do a correlation study, you're not actually showing causality. You can't say that for sure the age of the car determines the price. All you can say is that there is a connection between the age and the price. One of the reasons we can't say things for like the causation for sure is because there could be other things going on. One of the big things that could be a lurking variable. So a lot of times there are going to be strongly correlated connections because they're actually both connected to some other variable. And that other variable is usually called a lurking variable, and it actually causes the changes in both the variables that we're looking at, even though they don't directly cause each other. So there's things like a lurking variable causes changes in both variables, and that can be what makes them look strongly correlated. They're strongly correlated because of their connection to some other variable. So just because we show a connection, association, does not mean we show what causes what. There's one classic example. This is a fun one out of the book, so I want to share it with you. So there's a stork population and the number of human births in Copenhagen. For a period of time, the data, if you look at the data, suggests a linear correlation. So it shows a connection. So it looks like the more storks, the more human babies. And of course, it's because the storks are bringing the babies, right? That's the old, the old, cartoon, representation, kind of the old fairy tale kind of thing. In this case, there's actually some other variable that was making the connection. It was the fact that when you had an overall increase in population, you had more people, so more babies, and in this Copenhagen town, that meant more thatched roofs, which were great habitat for the storks. So there was something that was connecting both those, making both better, is just a larger population of Copenhagen. People were moving into town for whatever reason. And since there was more people, there was more babies. And since there were more people building thatched roofs, there was more storks. There's better homes for them in that town. So that's a lurking variable. This other thing, this thatched roofs and the population growth, that was the cause, not the storks weren't causing babies. Even though if you look at it and graph it, you'd see the strong correlation. The more storks, the more babies. Oh, obviously the storks are causing babies. No, that's silly. So you got to be really careful about that causality thing. And this is something I've seen even with people with PhDs, maybe not math, but PhDs, they do this mistake. They see a connection between two things, and they assume one is causing the other, and that's something you really got to be careful about. And this is what dietitians we're trying to fight all the time, is people assuming that one thing causes another just because there's some connection. Another thing you want to really avoid working with correlation is data based on averages. So if you do averages, they suppress variation, and then they could actually inflate the correlation coefficient. So they did a study once and they showed a correlation coefficient of 0.4, but then they went back to the study using regional averages. So instead of using all the data, they kind of took the averages for different regions, and they increased the correlation coefficient all the way to 0.7. Now 0.4, you'd say, oh, it's not correlated. It's not even half, 50%. But at 0.7, that's 70%. You can say, hey, that's pretty strong correlation. It was the same data, but the way they worked with it, they worked with the averages from different regions instead of just working with all the numbers they collected. So you really want to avoid this. You don't want to work with averages. So averages suppress individual results, and they may inflate correlation. They don't always inflate correlation, but they definitely can. Okay, so this was just, so far we're talking about the correlation coefficient, what it is. We figured out how to find it with the ln-reg a plus bx. Last thing we want to do is we want to take a sample and the linear correlation from a sample and be able to make kind of a assessment about the entire population. Again, when we collect sample data, we're not looking at the entire group, we're just looking at one little piece. And so that's not enough to say for sure right away things about the population, but it can lead to conclusions about the entire population. So we can make inferences. So we're using the correlation coefficient R for just a sample and figuring out what it is and looking at the correlated. But we want to do a hypothesis test to show that the populations, the two variables, the populations of the variables are correlated or not. So we're looking at the populations now. So we're going to have to do a hypothesis test. So when we're doing this test, we're using the correlation coefficient R as an estimate for the population correlation coefficient rho. Remember, that's for the entire population. So this parameter value for the whole population, we'll use R as an estimate for rho. Now there's going to be these four different things you'll note. First off, rho equals 0 shows that the correlation, there is no correlation. Remember that 0 means there's no association between the variables. This will be our null hypothesis. So our null hypothesis is that there is not correlation. Remember, you can never prove the null, so we can never actually prove there's no correlation. What we can prove, though, sometimes is that there is correlation, because we'll have strong enough evidence to do that, because the alternative will be one of these three. Those will be the alternative hypothesis, And you can sometimes find proof or evidence to support the alternative hypothesis. In this case, you'll either be able to support that the rho is greater than 0, which means we have positive correlation. Rho is less than 0, which means you have negative correlation. Or rho is just not 0. If you just prove it's not 0, you didn't show if it's positive or negative, you just showed it's correlated. So sometimes I don't care which way it's correlated. I don't care if it's positive or negative correlation. I just want to show this correlation. So I'll do rho not equal 0. But if I want to show positive correlation or negative correlation, then I would use those ones. Now, to do a hypothesis test, we always have to have a test statistic. As we've seen in the past, we won't really calculate this test statistic by hand. You could if you wanted to. It just takes r and r squared. So if you have those values, it's not that big deal. And n. Degrees of freedom, this one is actually n minus 2, and this is a t distribution when you're doing these r correlations. Again, I'm not going to really use this because we'll just use technology to get this. There is both a critical value and a p-value method. If you use technology will be used for just the p-value method. So if you're using technology, that's when you'll get just to use the p-value method. Now, they do ask in the homework a couple times about the critical value method, so I'll show you how to use that using the table. So we'll do that once. But first, let's go ahead and just do one with the technology, just so you can see how it works. So we want to do a correlation t-test. We're looking for correlation, and as a t-test, we're going to do it at the 5% significance level. Given the data provided, so give us some data on here, see if it is a linear correlation. So if there is a linear correlation. So remember the null hypothesis, so the null here would be there's not, so there's not correlated, that'd be that rho is equal 0, so that's no correlation. And so since they're just looking for correlation, they say positive or negative, the alternative would be that rho is not equal to 0, and that is correlation. There's connection between the data. Okay, to do this, we're going to make this data list 1, this data list 2, and then we're going to run a lin-reg t-test. So first off, let's type that data in our calculator. So I'm going to go to my stats options, edit, clear this out. I'm going to use the clear button. Just clearing this out. List 1, 1, 0, 4, 5, 5. Get that in there. List 2, 7, 4, 2, negative 1, 1. Okay, we got my data entered in, and then we're going to go to stats, tests, and if you scroll all the way towards the bottom, there is a lin-reg t-test. I kind of shortcut because if you go up one, that goes to the bottom. The lin-reg t-test is the one we want. Make sure that your X list is going to be my list 1, because that's where I put my first list. My Y list is list 2. Frequency would just be 1. You can just leave it like that, or clear it out. This would be your rho, and so in this case, rho we want it to be not equal to 0. So we make the rho not equal to 0 because that's our alternative. And we calculate it. It's supposed to be a rho. There we go. Okay, so from that, they give us a test statistic t. So the test statistic is negative 2.67. They give us a p-value. The p-value is 0.075. They did tell us the degrees of freedom, which, if you count this, 1, 2, 3, 4, 5, minus 2 gives you 3. That makes sense. It does tell you what the R value is. So the R value of this is negative 0.8, which you can see negative 0.8, that's a pretty strong negative correlation. But this one, I believe, since our p-value is actually 0.07, and we want to do this at the 5%, it's actually not strong enough. So this one, our p-value of 0.075 is bigger than our significance level, alpha, of 0.05, so we fail to reject. If we've been doing a 10% chance, a 10% test, we would have rejected. But since we were doing, let's reject, I'm trying to talk right at the same time. Since we were doing 5% level, this 0.075 was just not strong enough. In fact, if you look at this, so if we graph this, again, we're going to have to zoom it, right? So let's do zoom stat. You always have to rezoom every time you do a new stat graph, so zoom 9. You can see that there is some correlation here, but there's not very many values, so it's not super strong correlation. If we'd had more values in the middle connecting this, or maybe if these values were closer together, making a nice straight line, then we probably have enough correlation. But there's enough difference variance in here that it's not strong enough to actually say they are associated. It looks like they would be positive or negative associated if they were, but there's just not enough association there. More points making this trend probably would have made it better, but since there's not very many points, this is pretty wobbly for that few points. Okay, that's the p-value method, right? So if you find the p-value, you can just compare. So if they just want you to do a correlation test, then p-values works. This is great. You can just do this. But there are some questions where they might ask you for the critical value method. So this one, we're actually going to look at the critical value approach instead of the p-value method. So you got to be careful if you're doing the critical value to do that a little differently. So the critical value approach, again, we're going to think about if there is a correlation coefficient. So it is a correlation that gives the significance level. That's our alpha and the correlation coefficient. So again, we're thinking about rho not equal 0 would be our null, or sorry, our alternative. And our null would have been the rho equals 0. And again, the null is no correlation. The alternative is yes, there's correlation. This one, I'm using the same data, so we should be getting the same result, but I just want to show you how to do it with the critical value method. Now, to do critical value method, we are going to use a chart to get our critical value. And the chart we're going to use is actually a new chart. This is one we haven't used yet. It's in my lab, so you can look it up in my lab. It's the critical values for the correlation coefficient R. So this is a chart just for doing this one thing. That's the whole chart, just for this. So if you want to do critical values instead of p-value, you're just doing, the correlation coefficient hypothesis test, this is the chart for this. Now, in this case, we have degrees of freedom. Remember, you take the count here, 5 minus 2. So degrees of freedom is 3. 1, 2, 3, 4, 5. Yeah, it's 3. But, I forgot to mention, this is the degrees of freedom, but the chart doesn't use degrees of freedom. So this is one of the charts where you got to be careful, because you look at the degrees of freedom, and you think, oh, that's degrees of freedom. There's no 3 on here, but it's using sample size. So I always forget that, so I'm going to cross this off. I did the same thing last time I did this, so it's it's ridiculous how often I forget that. So in here we use n for the chart. So that's one thing you don't have to worry about. You don't have to worry about finding degrees of freedom because this chart is designed just for this. So we're going to use n for the chart. So n is going to be 5 because there's 5 in the sample size. So that's 5. So n is 5, and then we can do either a significance level of 0.05 or 0.01. And so this one's wants a 5%. So we're going to do n is 5 and 5% significance level. So the critical value is 0.878. The critical value, so n is 5, and alpha equals 0.05. So the critical value is 0.878. So that's how we get the critical value. Then we need to compare that with the actual R value for this. So we find R using the Lin-Reg A plus BX. So we'll find R. So that's our way to find R. So we just go to stat, calculate Lin-Reg A plus BX. Now we'll calculate R value. And we see that R is negative 0.839, which not a big surprise because, again, we're using the same data as last time, and it actually did give us that when we did this last one, because that Lin-Reg t-test actually gives you the R value as well. So that's actually another way to find R value. It just takes more time than doing this A plus BX method, because the A plus BX method, all you have to do is type in the data. As long as you have your stat diagnostics on, you get the R value that way. So that's what I think would probably be the faster way to get it. Okay, we got R, we got the critical value. Remember, with critical values, you're always looking to see if you're beyond it. So if I think about my distribution, and we say we have our critical values, in this case, the critical value is 0.878, or you have both your positive and your negative. So we would look at negative 0.878 and positive 0.878. These are critical values. And we say if your value is inside the critical region, then you would reject it. So we look at our negative 0.839 and we say, well, that's not far enough negative. So negative 0.839 is actually bigger than that negative 0.878. This one's more to the negative. So it actually lands in the middle here, negative 0.839. Your test statistic, because that's the R value reason for a test statistic. Since that guy falls in the middle region, we fail to reject. This is our critical value. This is our test statistic. So that's the idea. With critical values, you always mark off the critical regions. Here, because this is a two-tailed test, not equal to, we have two different tails. We got a positive number from this, but this gave us just the right value. So you get the negative, you just swap it to get a negative, and that's the other one. If you're doing a right-tailed test, you just use it as it is. If you use a left-tailed test, you swap it, get the negative, and that would give you your critical values. So this one, we had to look at the critical value, and we had to check, is that value outside the region? Well, it's not. It's on the other side, so we failed to reject it, which we already knew because we're using the same set of data from the p-value method. And again, you only have to do this if they tell you to use the critical value approach, and only if they really make you find the critical values. And I think there is like one homework question where they make you find the critical values, and then you have to use the chart for finding those critical values. So that's why I wanted to make sure I showed that to you. I don't believe I have a question for finding critical values. I can't promise that because if you two wants to look at the test, but I'm pretty sure most of the questions in the test are going to be probably let's use the p-value method, which is I think the more important method. But it's good to know how to use the chart just in case, especially because you'll use it for the homework. So that's it for 10.1. So 10.1 is all about doing these linear correlation coefficients. The R value that shows how strong the correlation is, and then doing the Lin-Rich t-test. That's a way to check and see if we have enough correlation in our sample to say that the entire population has a correlation. The next section, 10.2, we'll talk more about how to get the line of best fit and what that means, how to calculate that kind of stuff. So I'll see you on the next time.